Hi everyone, this is Professor Mayunger and you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to perform CFD aerodynamic analysis of a Formula 1 car using SolidWorks flow simulation. You can see this is the model. It is consisting of several parts. It is actually assembled. This is the main body. This is the person seated in the Formula 1 car, 4 wheels. This part is known as the nose and the back part is known as wing. All these different parts we have assembled, and finally after assembling the Formula 1 car we have fixed that one on a road surface, right? You can see the wheels are also rotating. Here in this analysis we will provide some kind of rotation of these wheels. First of all, we need to create the flow simulation environment using flow simulation wizard. Let us start it from wizard, and we are keeping the name of the project as a default project 2. We can name this one as power comment. Let us keep the name of this one as a default project 2, and next to that we need to select different unit systems. As per normal practice, we are considering this one as SI system, and we can select the different units as power comment, right? Let us consider pressure as Pascal. As this one will be moving with high velocity, let us consider this velocity to be kilometer per hour. And though temperature is not having any effect in this case, anyway, let us change the unit of temperature as degrees Celsius as per normal practice. Next to that, we need to select what type of analysis it is. Definitely it is an external analysis. And next to that, from physical features we need to select fluid flow conditions, and gravity will be involved. Let's see the direction of gravity in this case, as it is given by the direction here itself, y. The direction of gravity is y, so along y it will be minus 9.81 meter per second square, and along z it will be 0. And rotational conditions will provide from boundary conditions. So let us move on to the next one, and from gases we'll select air as the default gas. Next to that, default wall thermal conditions, the roughness we are considering, and finally we need to select thermodynamic parameters. Pressure is 10135 Pascal and temperature is 20.05 degrees centigrade as the default one. And these velocity parameters from initial conditions are very important, right? Let us see this one. Let us see how this is important. You can see this is the model. The Formula 1 car will be moving along x direction, so air will be moving opposite to that direction, right? Actually in this case velocity of air is main factor, because as the car is moving in the x direction, so we need to consider velocity of air in the opposite direction of x. Let us consider the car is moving with a velocity of 200 km per hour. In that case velocity of air will be minus 200 km per hour, right? So we can provide this one. It will be in the x direction. Here in this case we need to consider velocity of air. You can see here car is moving along x direction, so velocity of air will be in the opposite of x, so we are considering this one as minus 200 km per hour. With this one, let us finish this. Now you can see this is the computational domain, right? We need to edit this part, because less the domain size, it will take less computational time. Okay, let us edit this part. We need to decrease the computational domain. Up to this one is okay, and you can check it from this side again. It appears okay, so done. Let us hide this domain. Now we need to apply boundary conditions, that means the rotation of the wheel. One initial condition is already provided, that is the velocity of air with the value of minus 200 km per hour, right? That is provided. Now we need to provide the velocity of the wheels. We can provide either angular velocity or linear velocity also, right? Actually in this case the car has to move in the forward direction with a linear velocity of 200 km per hour. So if we want to provide the angular velocity of the wheels, so we need to calculate accordingly, because that angular velocity can be converted. In that case radius of the wheel is also provided. We can calculate accordingly, but to avoid some kind of confusions, we'll directly provide the linear velocity of the wheel instead of angular one. If we want, you can calculate this one accordingly and provide angular velocities, right? Ultimately, it has to move in the forward direction with a velocity of 200 kilometers per hour, right? So from boundary conditions, insert boundary condition, and it will come from here, walls. It will be one motion, and we're considering real wall. We need to provide linear velocity of 200 km per hour. As the wheel will be moving with a velocity of 200 kilometers per hour, accordingly, the path also will be in the opposite direction with the velocity of minus 200 kilometers per hour. So the velocity of wheel and path will be exactly equal but opposite in sign. Let us select the path or the road. That one will be moving with a velocity of minus 200 km per hour, right? Done. Green check. Now we need to provide velocity of the wheels. It may be either angular velocity or linear velocity. Again, insert boundary conditions, and from walls we need to select wall motion, and it will be real wall. In this case, as we told before, it will be the linear velocity of the wheels, or you can say angular velocity of the wheels, right? So we can select, it will be having same velocity of 200 kilometers per hour, and as the car will be moving in the x direction, so the velocity of the wheel will be positive. If you like, you can convert this linear velocity into angular velocity. Now we need to select that wheels. You can select the wheels from here itself. All the 4 wheels selected, and these wheels will be rotating with a linear velocity of 200 kilometers per hour. Okay, green check. It is done. So all the boundary conditions applied. Now we need to select some goals. So insert goals. It will be global goals, and excluding global goals, we can find some kind of surface goals also. Let us consider some global goals like average total pressure. It will be average velocity, and excluding that, we can find something else like normal force in the x direction, normal force is in y direction. By the same time, we can find some other things like frictional forces also, average frictional force. These are the different goals we are trying to find out, right? So green check. These are the global goals. Excluding that one, we can find some kind of surface goals also. That means we can find different parameters like pressure, velocity, etc. at different surfaces. Okay, so insert surface goals, and we need to select some specific surfaces at which locations we need to find out velocity, pressure, etc. Let us select different surfaces from the geometry itself. This is the main body. Axle also we can select both the axles, supports, wing, that is the back side, nose, that is the front side. Let us select wheels also, that will provide velocity, pressure, etc. at different locations, and driver also. We have selected all the parameters, and we need to find out summation of all these things together. If we want, we can create separate goal for each of the surfaces also, but let us avoid this one. We want to have accumulated one, right? We need to find average total pressure and average velocity. Green check. All the goals determined. Now we need to mesh it, starting with mesh, and we're going for manual meshing. And here in this case, we will refine this one up to level 3. Let us see the refinement level. You can see we are having actually up to level 1 refinement that can be modified up to level 3 to have better results. So green check. Meshing is done, right? Now we need to go for running this one. Let us run this simulation. We are running with new calculations. Let us run it. You can see simulation has already started and initial calculations are going on. can see the results from here itself, from the solver window itself. Let us see what is going on inside, right? Let us view velocity distribution, and from image attributes you can select the higher resolution one. It has started only. As time will proceed, you can see the different colors at different locations. You can see it right now. You can see this is the location of the Formula 1 car, and here in this case you can see some different colors are available. This is actually showing velocity distribution in kilometers per hour. At time will proceed, you will see different velocity, pressure distribution, etc. Right? Now it is clearly visible at this moment. The velocity parameters of profile will be prominent as time will proceed. You can see the color distribution at different zones, indicating different velocity ranges. And at the top side, you can see here itself, the color is red, that means velocity is very high. And at the bottom side, velocity level is mixed zone, green and blue zone. Blue zones means velocity level is very, very less, right? Let us see this one. We can proceed from this side. Instead of velocity, you can see some other things like pressure distribution also. Let us view that one. Front end, and instead of velocity, we'll see pressure distribution, total pressure, right? This is pressure distribution. Till now, we cannot see that much of changes, but as time will proceed, you will see different ranges of pressure, velocity, etc. at different zones, right? Let us close this, and we can move on to that velocity again. This is the velocity distribution. Now we can see velocity from other planes also. Let us view it from here. We can change the orientation from front plane to right plane. And from image attributes, we'll change the resolution from existing one to a smaller one, right? Let us take this one to 640 by 481. Yeah, this one from front plane. This is pressure distribution. We can change it to velocity 1, then we can view it in a better way, right? So from right plane, instead of pressure, it will be velocity, and image attributes will say 640 by 480 resolution. Okay, done. See, can bring this one this side, then you can understand this one better way, right? Let us make this a little bit bigger one. Resolution will make it bigger from right plane, and velocity distribution, image attributes, it will be 800 by 600. Let us see this one. Yeah, fine. So we can see velocity distribution from right plane and also from front plane. This one is actually from right plane and this is from front plane. As time is proceeding, we can see different color zones at different regions, indicating velocity at different zones, right? So in this analysis, our main aim is to reduce the drag coefficient or drag force. Drag force actually a force in the x direction that to be reduced. As a global goals, we have already determined force in the x direction, that will be actually drag force. Excluding that one, we could have determined like drag coefficient, and that can be obtained from the equation goal. But at this moment, we are not providing. We'll show how to find out this drag coefficient in a different analysis. Okay, so it is clearly understood that at these regions, velocity is very less down this part when air is striking the Formula 1 car. At that location, velocity is 0. You can see this is as per normal rules. At boundary, when air is striking the Formula 1 car, velocity will be 0. and at different boundary layers velocity is different, and at this location you can see velocity is very high, right? Now solver is finished. You can see the results from different cut plots, right? Let us see all the results are converged or not. You can see here from the solver window itself, you can see all the results are converged, and that is visible from this green color. So you can see here velocity in x direction and also frictional force, normal force, etc., right? So those values we'll see later on from the graphs. Let us close this one. We'll move on to the results, right? So results, first of all, we'll see cut plots of velocity distribution from front plane. So inside cut plots, it will be velocity distribution from front plane, contours of velocity, and along with contours we want to see iso lines and streamline also. Green check. So this is the distribution, you can see in a better way by using the animation. So let us see the animation of this one. You can see it from specific planes. You can see at different zones, different velocity ranges are available. We can view these things in a different way also, right? Let us close this, clear and hide this one, and we'll edit these cut plots. Number of labels will make it to 20. And here instead of streamlines, we'll see here line integral configuration. And here itself, we select all the sim parameters, and we want to see vectors also. Now we can run this. Let us clear and hide this one. Now we'll do one thing. Instead of all these parameters, we'll see the iso lines that will show the actual distribution of velocity where the ranges are actually high actually, right? So cut plots, edit definition. Instead of considering all these different parameters, we'll select only iso lines, right? Green check, and let us play. To understand this one a bit, let us play it. So we can see here velocity at this region is very high at the top side. It is in the red zone, which is in the range of 230 to 253 kilometers per hour, and down level you can see it is in the range of 160 to 207 kilometers per hour, and down this one you can see it is blue zone. That means it is in the range of 0 to 46 kilometers per hour here itself, right? We'll see one thing, instead of seeing velocity you can say pressure distribution also, right? Let us change it to pressure distribution. It is pressure. Let us see it. This one is showing pressure distribution along front plane. We cannot say that much of variation in pressure. It is there, but not that much. But velocity distribution, you can see it is huge amount of variation is there. Now what we'll do is, now we'll change the orientation and we will see these things from right plane, right? So let us clear and hide this one, and we'll see this one from right plane. So LED definition, and we'll view these things from right plane. Instead of pressure, want to see velocity distribution. Okay, go and check. We need to change the orientation also. From right plane, we'll see this. Let us view this one in the form of animation. Let us play it. You see how this is actually varying, right? Up to this surface, velocity was little bit variable, but after that, it is streamlined actually. We have made the path little bit of curved one willingly. You can see velocity distribution along the Formula 1 car. The aim of our analysis is to reduce the drag force, and for reducing the drag force, we need to optimize the design. That can be done later on. Using structural analysis, we can optimize the design, right? By seeing the results of this CFD analysis, we can change the different parts. Why we need to reduce the different parameters, and that can be done using structural analysis or structural optimization. Okay, let us clear and hide this one. Instead of that one, we can see pressure also. Let us change it to pressure again. From right plane, we'll see pressure distribution. So we cannot say that much of changes in pressure distribution, right? So let us clear and hide this one. Next to that, we'll see surface plots. That means different parameters at different surfaces, right? So surface plots, insert. Instead of pressure, we want to see velocity at different surfaces, and we can select equal surfaces. Suppose here at the front nose or at the back wings also you can select, or if you like you can select the whole body also. Velocity at the surface where the wheel is known already. It is moving with 200 kilometers per hour, so we are not providing on that surface. Let us provide some specific surfaces, or you can select all surfaces from here also, but we don't require. Let us select some specific surfaces, and on that specific surfaces we want to find out our different equal parameters. Let us select all surfaces, and we need to find out contours of velocity. Right, you can see we have selected all the surfaces. We can check it right now. Surface plots, we have selected all the surfaces, right? As I told before, the wheel is actually moving with a velocity of 200 kilometers per hour. By the same way, the road is also moving in the opposite direction with a velocity of 200 kilometers per hour. So these are already provided here itself, velocity of road and wheels, and excluding that, velocity of the Formula 1 car body is actually 0, but other locations it will be different, right? Let us see pressure distribution also. Instead of velocity, we'll see pressure distribution. You see different values of pressure at different zones, right? Let us clear and hide this one. Next to that, we'll see dynamics of flow particles at any specific surface or a specific location. You can see how the flow particles will move, right? Insert flow trajectories, and we'll see this from specific surfaces, right? We can view it in the form of rectangles, line, or sphere. let us select rectangle, and we're going to see in this form of fives. Instead of static appearance, we're going to see dynamic appearance. And let us consider all the parameters default, and instead of pressure we'll select velocity. Green check. This is actually velocity distribution. Now we can make the numbers more and see in a better way. Let us edit this one, flow trajectories, edit definition, and instead of these 20 numbers of particles, we'll make it 200 numbers, right? And instead of arrows, we'll make it spheres, and let us see it. See, now we can animate this one, flow trajectories. Let us play. This representation, actually I don't like it. It is better to see this one along a specific line that will provide a better results. Let us close this one, clear and hide, and want to view these things along a specific line. So edit definition. Instead of rectangle, we see along a line. Let us drag this line near to the Formula 1 car body. We can drag it as per our requirement as any specific location. Okay, green check. Now along the line, let us make the numbers instead of 100 numbers. We can reduce these numbers. Instead of spheres, we can make it arrows. Let us see it. Green check. It is generating. Now it will be understood in a better way. Let us view it in the form of animation. We could have changed the computational domain. Our computational domain actually is high, that's why flow is occurring down this path also. So we should have made the computational domain started from this down surface, right? So computational domain we should have changed. You can see here is clearly understood how the flow particles are moving through the Formula 1 car body, right? Let us close this one. Next to that we will see our goal plots. So insert goal plots, and we want to see all the goals. Let us select it from here itself, and instead of seeing it here itself, we can transfer all these results to Excel and can have better analysis results. Let us export it to Excel to see the results individually. This is consisting of all the results. You can see the results. This one is actually the total pressure. You can see after 120 numbers of iterations, you can see pressure is a little bit high compared to normal atmospheric pressure. It is 101,821.76 Pascal. Next to that, you can see frictional force. Again, after 120 numbers of iterations, frictional force you can see 2.35 Newton. Next one is normal force along Y. It is again after 120 numbers of iterations, it is 0.947 Newton. And next one is a one global goal, that is normal force. Finally, you can see here average velocity after 120 numbers of iteration. Here it is. Average velocity is actually 196.942 km per hour. And the last part you can see average total pressure after 120 numbers of iterations. Average total pressure is actually 101 Average total pressure is 10316.76 Pascal. Now all this data can be obtained in the same place from SolidWorks also. Let us view all these things results. Let us show it. You can see all the results here itself, right? Now all the results can be seen from the summary itself and from history in the form of graphs, right? These are all the results what we have seen already before. First one is average total pressure. It is 103,161.766 Pascal after 120 numbers of iterations. Second one is average velocity. You can see it is minus 196.94 kilometers per hour. And third one is normal force along X. It is minus 7.3 Newton. Then fourth one is actually, you can see normal force along Y. It is 0.947 Newton. Next one is frictional force. After 120 numbers of iteration, frictional force is 2.35 Newton. Again, you can see different parameters like total pressure and total average velocity. Total pressure is actually 101,1822.39 Pascal, and finally average velocity is actually, you can see, 119 kilometers per hour. So these are the different results you obtain from this analysis. Now this is all about our analysis. Instead of stopping it here, we could have done something else, like we could have started some kind of equation goal, and in that equation goal we could have found the drag coefficient, because in this CFD analysis our main aim is to find out the drag force and that to be reduced to have a streamlined motion. Okay, so with this one we'll conclude our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.